Good afternoon, everyone. Woo. Is everyone having a good conference so far? It's amazing, isn't it? Absolutely amazing. Well, thank you all for being here. Thank you for coming to my talk. I wasn't expecting to be in quite as big a room as this one, so I was expecting just to have a few people to talk to and have a nice, intimate chat about something that I love, but thank you. So today, I'm going to be talking about path tracing in 3 ways, a study of C++ style. This was an idea I had 6 or 7 months ago about a talk that I could give here, and let me tell you a story. So often when people contact me, they will ask, how do you learn programming languages? I've seen you do C++, I've seen you do low-level stuff. How should I learn this kind of thing? And my sort of go-to answer for this has always been, find something that's relatively short, that's super cool, has like some instant feedback, and write it in that language. I learn by doing. I'm sure many of you do too, right? You can read as many books as you like, but until you actually sort of sit down and start typing on a keyboard and experience usually the horrible compiler errors and things, then you don't really get a feel for the language and how everything fits together. So I've used this technique myself when I've been teaching my kids how to program in Python. So this looks very familiar to one of Ben Smith's slides. If you remember, he had an ASCII Mandelbrot generator. And it was pretty effective. It was very short, a couple of lines of code, and I could explain what everything was, and that was cool. I also used it to teach myself how to program in JavaScript when I wrote a BBC Micro emulator, which is an awful lot of fun, incidentally, so I wholeheartedly recommend you doing an emulator or something like that. And so when I was thinking about this talk and how much C++ has changed over the years that I've been programming it, I decided that I would try to look at C++ through like a new lens by writing different styles than my natural style and basically taking my own medicine and apply my idea of writing something to learn a language to a language that I already knew. Before we go too much further, I want to be absolutely clear. I'm just a sort of grunt, run-of-the-mill programmer. I am not like an expert in any sense of any of the things I'm going to be talking about, so feel free to leave right now if that doesn't float your boat. It's not expert advice. Anything I say nothing I say will be considered to be expert advice on either path tracing or C++ code styles in general, and absolutely it is not one style is better than another style, as you'll see as we go through. What it is, though, is my interpretation of what those styles are, and it is real code. You can go to GitHub and find this right now and have a laugh at my expense. And above all, I hope this is interesting because I love this kind of stuff and fun. We'll see. What styles did I pick? Well, the first one's a bit of a cop-out. This is kind of my reference style. This is how I write code naturally already. Mostly it's object-oriented, and so that's one of the 3 styles I picked. What do I mean by object-oriented? I mean that the data and the code are tightly bound together, and if I need to have things that behave in different ways, I'll use like virtual methods and inheritance to have polymorphism. The second style I picked was functional programming. And I realize this is a kind of a difficult thing to say. It means a lot of different things to different people. But my interpretation is to separate the code and the data and have mostly immutable data that is transformed by a sequence of functions using techniques like passing functions to other functions for polymorphic type behavior. That means using variant types and other sort of algebraic data types like optional, and some of the other cool things that are coming in the language soon, actually. And the third style I chose was data-oriented design. This was kind of a hot topic over the last few years. When I was doing the research for this, I saw that there were a couple of talks over, I think in 2017 and 2018, both talking about data-oriented design. And when I sort of looked into it, it sort of felt a bit like old school C programming to me. My background was programming video games, and that was all about this kind of thing. So what data-oriented design is sort of starting from the bottom, from the very base components of what operations do I need to do, and then designing my data structures around those operations so that they're efficient for both cache usage, branch prediction, and all those good things, and then sort of building my way up. So whereas object-oriented and functional are top-down, data-oriented is more bottom-up. You might be asking what path tracing is, but thankfully, Ben Smith has already shown this image earlier in his keynote when he was demonstrating the amazing web compiler thing he has. Has anyone heard of a web-type compiler thing before? I've never seen one before. So this is an image that's generated by Kevin Beeson's small PT. So I picked path tracing because I'd done it before, actually, when I was learning Go and Rust. And it's provably small because that image is generated by 100 lines of C++ code. Now, you don't really want to look at those 100 lines of code because they're a bit squished in, but it's not terrible code if you run it through Clang format first, of course. So what is path tracing? Path tracing is a way of making images. It's very similar to ray tracing, and I'm going to put a big caveat here that, again, I'm no expert at this. I've read a few books, and this is my interpretation and distillation of those concepts. But we have a scene, in this case, a beautiful red sphere. There is a very bright light sphere up in the corner. We have an eye point where our virtual camera is going to be, and then we sort of project a screen. This is where all the pixels of the screen are in that space. And for each of those pixels, we're going to fire a ray from the eye through that pixel and see what it hits. In this instance, it hits the sphere. And now we say, how could light have got to this part of the scene? How would I know how bright this is because of lighting? And this is where path tracing and ray tracing sort of separate and diverge. Because in a traditional ray tracer, what you do now is you look at your big list of lights and you see which of the lights could possibly have reached you by casting a ray to the light specifically. In path tracing, we say, well, the light could have come from anywhere. Light bounces around. It's one of its defining characteristics. So we won't just restrict ourselves to looking in the direction of lights. Instead, we look at the surface where we hit, we put a sphere, a hemisphere, over that point, and we say, let's collect all of the light that comes in to this point and then see how it would interact with the material, and that's the amount of light that would bounce back towards the camera. Well, it turns out it's a really, really, really difficult problem to solve, and there's no sort of analytical solution. So the pragmatic solution is we pick a random direction and we start looking in that direction. So we then look down that ray and then we carry on the process. So this is a very recursive a very recursive process. And then because we did use some randomness here, we probably need to do it a few times just to sort of get a bit of a feel, a sample for it. And in practice, we'll do this like tens of thousands of times per pixel. And that's what makes path tracing both very, very slow, but also generate very good images. So in summary, for each pixel, fire a zillion rays into the scene, bounce them around randomly, accumulating the intensity and color, and then average them out, and then that's the color of that pixel. It's worth mentioning that lights are not actually special in any meaningful way in path tracing. It's just that some materials you might encounter are just intrinsically bright, and it doesn't matter how much light is falling on them, they will always be emitting some amount of light. So effectively, that first ray that goes in will bounce around the scene forever until it happens to hit something which is bright, which could be a long time. My path tracer is pretty simple. I mean, small point, the one we saw earlier, Kevin Beeson's one, is also simple, but mine's even simpler. I have extremely simple materials. I only deal with spheres and triangles, and the scenes themselves are defined in code, in terrible programmer art, so I apologize for the things you're going to see. And that's mainly because I had to write it 3 times, and there's only a limit to how much code I'm prepared to copy-paste. Incidentally, this kind of thing is a really difficult thing to do if you, like me, have been trained for years to like factor out common code because you're forever duplicating code, but on purpose. I've made you wait long enough. These are pictures that my path tracer can make. And it's really quite amazing because it's relatively simple. Like I said, I've pretty much explained the whole thing to you. And yet we get all these interesting effects, and I can't really point, but if you look up in the corners of the rooms, it's darker because there are fewer places that the light can bounce around to reach the corners. If you look at the left-hand side of the left-hand box, you'll see that it's tinted red because the only way that light can reach there is to have bounced off the red wall next to it, and similarly for the green side of the wall. So that's a very famous image that comes from, or a scene, from Cornell University, where they actually physically made a box called the Cornell box and sort of painted it and took very careful measurements, and it's used as a benchmark. It didn't have a magic shiny sphere in it though, but like when you've got spheres, what are you gonna make? The other image, incidentally, is the Suzanne monkey from Blender, Who here's heard of the Utah teapot? Yeah, so the Blender folks, so Blender is an open source modeling package. They issue the teapot in favor of this monkey, and I think I prefer it, actually. Just a quick note on the general approach. I didn't rewrite absolutely everything for all 3 versions. The math library I made, or maths, sorry mum. The math library has a vector class, which is essentially an XYZ. I said Z though. An XYZ, and the one Brit in the front row. And I have a norm3, which is a normalized vector. It's a vector that's known to be normal. This turned out to be a really cool and important thing during the development because now I could actually, in the type system, make some observations about things that were already normalized, which was pretty cool, and found some optimizations. I have a ray, which is a position and a direction. I have a hit, which is just a point in space, the normal at that point, and some other information. It's essentially just geometric. And then some other bits and pieces for materials and cameras, which I didn't want to redo 3 times. All right, let's go on with the first way. The first style is the object-oriented style, and I'm going to spend the most time talking about this because this will give the foundations for the other approaches. And in the other approaches, I'll be mainly pointing out the differences and the things that I thought were important. The major components of the renderer are how I store the scene, how we render it, that is like essentially just the main loop, the main of the function, radiance calculation. Radiance is the amount of light and light intensity flowing down a particular ray. And again, I'm going to wave my hands a lot here because if you look in the literature, it's all about per solid angle and other things, but we're just going to simplify for now. Materials, which is how the light interacts with a particular surface, so the material controls that aspect. And then the other aspect is having a ray, finding the intersection with the point inside the scene. Give the live captioner a little break there. Right. There's going to be a lot of code. Sorry, I forgot to warn you. This is a very code-heavy talk, but I'm going to have to get through it because I want you to see the things at the end. So this is what my scene looks like, or rather, this is an object that's in my scene. And in the object-oriented version, of course, what I'm going to do is have a virtual method. So this is how I'm going to dispatch based on the different types of objects that could be in my scene. This intersection record is something that sort of says something about where the ray intersected and the material that was at that point. And here I'm returning a bool saying whether this particular ray intersected this particular piece of geometry, and if it returns true, obviously, if it did, false if not, and then if it did intersect, it fills in that intersection record. I'll be honest, the first time I wrote this, I used the std optional because it's the absolutely obvious thing to put here. But when I then went on to start doing the functional programming version of this, I realized that std optional is kind of a function-y thing. And so in order to sort of slightly caricature each of the styles, I actually backed it out. And in doing so, introduced about 3 bugs. So std optional is great, right? Our render loop looks like this. And I'm sorry if Sean Parent's anywhere around here. There are lots of raw loops here. We've got for all y, for all x, for all samples, I'm going to generate a random ray that passes through this particular pixel on the screen. Now, as I said, there's going to be a lot of samples. We're using a lot of randomness here. The degrees of freedom in the camera are within the pixel itself, which gives me a little bit of anti-aliasing as I randomly pick somewhere within that pixel, but also it takes into account the parameters of the lens of the camera itself. So if the aperture is wide, then things off in the distance will be very, very blurry because the samples will wiggle around all over the shop. I realize this is not technical terminology. Anyway, we get a random ray. We say how much light is coming down that ray. We add it all up, and then at the end of it all, we average it out and plot it at that point. Okay. How do we work out how much radiance is coming down a particular point? Like I said, this is very, very recursive. So the first thing we're going to do is have our sort of base case for recursion. At some point, we have to give up, otherwise we'd be here forever. If we've reached the limit of recursion, we say, well, there's no light coming. Bit of a cop-out. There are some clever things to do, but this is not clever code. We ask the scene if this ray intersects anything. And although I haven't shown it, that scene code basically goes through the array of all of those primitives and finds the nearest one to the ray, the nearest intersection point, or none if there wasn't one. If we didn't intersect, then again, We shot off into space. We never saw anything. There's no light coming that way. If we did hit, we're going to do a little trick here. And this is something I didn't really talk about before. So this is the point where we've discovered that, that point on a sphere, and we're just going to pick a random direction. It turns out if you just do one sample, it's really noisy. Obviously, there's sort of a lot of randomness. We're likely to just miss the lights. We're a bit likely to get all sorts of speckly effects. So as a sort of concession to getting a decent quality image with fewer samples, on the first hit, I actually do multiple samples and I stratify them. That means that I'll pick some at randomly around the 3 o'clock direction, some at randomly around the 9 o'clock direction, and so on round, or 3, 6, 9, I can't count, sorry. But like that. And now we're in the inner loop of determining how much light is coming into this particular intersection point. We've got another loop, 2 loops there for all of the U samples, for all of the V samples. You can think of those as like polar coordinates. We fiddle them around with some randomness, and then we pick one more random number. That random number is then given to the material to say, hey, given all of this information, what kind of light might be coming out of you? The material will obviously need to go and call the radiance system again to say, well, I might only be bright because there's light coming in from somewhere else. So we have to give it a way of recursing. Of course, what I could do here is hand it the whole renderer again, and then all of the other parameters the renderer needs in order to keep track of where it is, but that wouldn't be very OO. So what I've done is I've made an interface class, which is this sampler, you can see, which kind of binds together all of the information and provides a very simple interface to the material to just say, hey, what light's coming this way? That's a virtual method as well, which hurts me, but we'll talk about that at the end. So anyway, we sample a few points around this material, and then at the end, we ask the material, based on these samples, what would the total amount of light be coming out at this point? This is essentially the point where something which is intrinsically bright can add in something extra here if it so chooses. How do we determine intersection? So this is an implementation of the sphere primitive, where you can see that we have a binding of a sphere class, which I realize is a confusing name. This is kind of like the Platonic sphere. It just has a position and a radius, and we can do geometric level tests with it. It doesn't know anything about being in a scene. And this primitive kind of binds it together with a material. We ask the sphere if it was hit by this particular ray, and if it isn't, we can finish there. Otherwise, we return an intersection record where we bind that hit information with the material. The interesting thing here is a more sophisticated primitive could actually pick different materials depending on where on the primitive you hit. So that's why it's divorced from the actual sphere object. All right, this is about the most hairy maths you're going to see. This is the intersection code inside the sphere. Effectively, we're solving a quadratic equation here. And if you can remember the maths, it's like minus b plus or minus 4a, square root of 4ac all over 2a. So there's a square root in there. And so this top bit is getting the bit that we're going to square root. But if it's less than 0, there is no square root. There is no real roots to the equation, which is, in this instance, means that we've missed the sphere. So at that point, we know we can bail out early. Otherwise, we take the square root, we do a whole bunch more maths, and we end up with a hit position, and we're done. Triangles are a bit more complicated. We're going to see them a bit more in depth a bit later on, but I'm going to gloss over them for now. Materials. There's that interface that I provided to the material to allow it to sample out. As you can see, it's a really simple interface. It just takes a vec3 and the ray and is expected to provide the material with the light coming that way. And then here's my virtual method for the material itself. It's given all that information and expected to work out by itself the light that's coming in. This is my badly named shiny material, which is a little bit shiny and a little bit not shiny. And that's where that p-value comes in. If you remember that random number that we picked, the randomness in this, incidentally, makes it really easy to add all sorts of things here because we can just use the law of large numbers and use the probability of randomness to sort of pick different routes through, knowing that eventually over all those things, it'll sum out to something that's going to be okay. So in this instance, we say, this material is partially shiny and partially diffuse. Now, I could shoot 2 rays off, one for doing the reflection part and one for doing the diffuse part, and then sort of balance them out like 20% shiny, 80% diffuse. But why don't I just pick one or the other and let probability work it out for me? So if that random number coming in is less than how shiny I am, I'm going to sample not actually in a direction like I described before, like 3 o'clock, 6 o'clock, 9 o'clock, but I'm going to sample off in a cone around the reflected point. That is the point where the light would have bounced off of this particular material and gone off. So a mirror would have a cone that is infinitely thin. So the only light I will sample for a pure mirror is the light that bounced exactly and came to the ray that we are tracing. But if I widen the cone out a little bit and use those U and V parameters to sort of pick a random point in that cone, then I start to get a sort of blurrier image. And that allows me to have things that are like slightly less polished than a perfect mirror. For the diffuse sample, we tint it with the color of the object itself, and then we do sample randomly in that hemisphere. Okay, we're done. That's all the code. I mean, mostly of the code. We can get some pretty images that look like this, and you can see all the lovely interactions between the lights and things, and that's great. That's really rewarding. You know, you write a bit of code and you get some feedback like this. Although, of course, as anyone who went to Barbara and Ansel's talk, what really happens is that you write a bit of code like this and you render it and you get a big black screen. And then you have to go, why is my screen black? Is my camera pointing up? Are my objects infinitely small? Is the intersection code not working? This is incidentally why we write tests. Which you all write tests though, right? What did I like about the object-oriented version? Well, it's familiar. It's how I write code naturally, pretty much. The code layout was familiar. The testability was good. Each of the objects could be poked at from outside really easily. I could instantiate the platonic sphere and fire rays at it until I was happy that all of the intersection with the sphere worked. I could make a sphere primitive, and I could use its virtual interface. I could do all these things. It really felt familiar to me, and I was able to get a pretty good test coverage. And the performance was pretty good. I was impressed. I haven't got time to go over all these things, but like the devirtualization that compilers can do these days is nothing short of amazing. Thank you, compiler writers. I can't do a talk without thanking compiler writers somewhere, right? What did I not like about this? Well, giving up standard optional was a pain and introduced a bunch of bugs. And arguably, I'm overusing virtual. When I gave an early version of this talk to my colleagues, they slapped me down for having given a bit of a bum deal to the functional programming and data-oriented design by caricaturing them, but giving object-orientism a lovely glowing right. So they said, well, why don't you? This should be virtual. That should be virtual. You should input them. Okay, and so this is the version you're seeing here. But I wouldn't naturally write that many virtual functions. Let's move on to the functional approach. Incidentally, this is an array of spheres, and at the top right-hand corner is the perfectly shiny version, and to the left it's the more blurry, and then from top to bottom it's it's actually the index of refraction. There's a lot more math that I'm not showing you here. So a note on the functional programming. I use ranges because I know they're coming, and I've just come out of Jeff Garland's excellent talk on ranges, and now I'm aware of how badly I'm misusing them, so please be gentle on me. So I'm using ranges because I feel that that's a sort of functional thing to do, taking data and sort of processing it through a number of views without necessarily mutating the original data seems very functional to me. I also used TL optional. Is Cybrand in here? No, all right. The TL optional library is awesome. It adds on some things that are more like algebraic data types. Again, things that I've, in other functional languages, come to sort of rely upon. You'll see them in a second. My clicker works, there we are. So the scene is stored very differently. Instead of having all of the behavior in the objects, I just have these pretty much boring structures with the information. Here, this material is not polymorphic, incidentally. I just store all the possible things that the material could be in one. I punted on that for now. And then the way that I get polymorphic behavior is I use a variant of the two types of things that I can have. The rendering is probably the biggest change. Gone are those raw loops. I'm very pleased with myself for that. And instead, and this may be a terrible misuse of the library, as when I was asking on the Slack over some of the error message I was getting, I think someone said, oh my God, this is how people are going to use the library, isn't it? Which I don't think is a positive thing. But we're going to get a view of integers. This is a view that just creates something we can iterate over that gives me the numbers 0, 1, 2, all the way up to height. And then we get a view of ints from 0 to width. And then we take the Cartesian product of them. What that means is that we'll get for all x's, for all y's. Oh, that's useful to know, isn't it? Whoopsie. LLVM9's out, incidentally, everybody. It's on Compiler Explorer already. We pushed it earlier. So anyway, that Cartesian product will return tuples of y and x, because that's the way round I did them. And then I'm going to pipe that through a transform. That transform is this I guess it's a capture, a closure here. I capture a few things, and then for every pixel, we're going to instantiate a random number generator. This is my concession to making this as sort of deterministic as possible. The random number generator is seeded by the pixel coordinates and the sort of sample that we're doing at the moment, so that it's deterministic, and I think I'm okay on the FP front, although I'm sure someone can correct me in a minute. Now, this is interesting because although we've created all these views with all these pipelines of interesting things, nothing's actually happening yet. Views are very lazy. It's actually the constructor of this array output class, which is effectively just a glorified std vector of pixels. If we pass a range into the constructor of the array output, it will just consume things until it gets to the end. And as it's consuming them, it fills itself in. So effectively, the construction of the output container is what causes all of the calculations to happen and for the results to be written out. And that's kind of cool. There's no actual mutable state anywhere. Similarly, when we're actually looking for the light coming into a particular point, we're going to do the same kind of trick. This is for all the U samples and for all the V samples. I've hidden the code for this because it's a bit ugly, but we're taking the integer count, 0, 1, 2, up to number of U samples, and turning it into a tuple of doubles that are randomized around like the clock face. And then we're going to calculate the radiance at this intersection. This is the equivalent of where the material stepped in the OO version. This is me saying how much radiance comes into this particular point in the scene based on these parameters. Of course, we still need a mechanism for letting the sample function here, this radiance at intersection, call back and get radiance from the scene. And in this instance, instead of passing a virtual base class, we're just going to give it a function. And this function will hold all of the information needed to call back into radiance, with the exception of us adding 1 to depth so that we remember that we're getting deeper through the recursion each time. Oh, and then we accumulate over it. Now, I think Jeff said that accumulate didn't make it into C++20. Is there anyone who can confirm that? But I'm using it anyway. Because again, these are all views inside this part here. Nothing would actually happen until I started doing something with it. And by calling accumulate, it will add them all up. And that's exactly what I want to do. This radiance at intersection function is pretty hairy. And so I'm just really highlighting here that recursion point here. The passing the radiance function allows this function to do its work and then also do more samples out into the scene. Intersection is where it starts getting interesting. So you remember that the base type of the primitive was a variant of all the things that could be. Well, it just so happens, if my clicker works, well, we need to visit it in order to find the actual type that's held inside that variant. But through careful design, or accident, choose what you wish, both primitives had a dot shape. And those shapes, although they're of completely distinct types, both supported an intersect method. So I'm able to use a template here to visit it, and that saves me writing essentially duplicate code. The interesting thing about the intersect method is now I am returning an optional. But importantly, it's that TL optional. And the TL optional comes with it a bunch of useful extra features. So the intersection, which I'll show you in a second, it has, it returns an optional intersection record. And then I call map on it. What map does is allow me to change the type of the thing that's held inside the optional, but only if the optional carried anything in the first place. So if there was something in the optional, i.e. if it was a successful hit, then my lambda is called with the contents of that optional, and I'm allowed to return a completely different type here. And the result of this will be an optional of the new type. If, on the other hand, it was empty, then just an empty optional of the new type is returned. And that means that I don't have to worry about ifing stuff and if this optional is set or continue and stuff like that. I can write fairly fluid code, and you'll see me chaining this in the next slide. Because this is how, once I sort of got this in the bit between my teeth and got excited about like how much this could change my code, I thought, well, I can actually rewrite how the intersection is done for the functional approach. So if you remember, we did that determinant thing, and then there was an if check that said, well, if it's less than 0, then clearly I can't take a square root of it. I wrote something called safe square root, and that returns an optional double. So if I can take the square root, I get a square root. If I don't, I get an empty double. And now I can write a nice chain of and thens and maps. So this will return either the square root or nothing. Now we look at this and then. And then is very similar to map, except it allows me to return an optional itself, which allows me to also opt out and say, actually, I failed at this point. Because there is, I didn't show in the other slide, there is this part here where there's some other checks that need to be done, even though I have successfully gotten a square root, and it still means I missed the sphere. So if it's too close to 0, then I have to say, yeah, you're about to blow up here. Let's just pretend it missed the sphere. Otherwise, as it happens, if you remember with quadratic equations, you end up with 2 solutions. I pick the solution that is nearest to the beginning of the ray here. And then I can map over that and say, well, okay, I've got a distance. Now I can go and do all the other calculations I need to do. It's all very neat. What did I like about this approach? I didn't really show it here, but I consted all the things. You know, while I was getting myself into the mindset of immutable data, I just went through all of the functions and all of the local variables, I put const in front of them. And I was surprised at how many times I just flippantly modified local variables when it was really unnecessary. So this helped. And again, this is not really a functional thing, this is just a mindset thing, which I think is an important aspect of doing this kind of thing. I think the code is clearer. I like the optional stuff. The ranges stuff, I'm on the fence about, but it's coming soon, so I'm sure we're all gathering more experience about how to use it well. Testability was about the same as the object-oriented version. I didn't like the cryptic compiler error messages. This is probably a fault of the user, as they always are, but every time I made a small tweak and something didn't compile in ranges, it was template hell all over again, which is not really the fault of the ranges library. I know, for example, when concepts come in, we'll get much better error messages, and it would help if I read the documentation instead of just assuming I could work it out by hitting Alt space or Control space, which is mostly my programming these days. I am a little concerned that I am doing something that is fundamentally not functional programming by passing the mutable random number generator around. It doesn't seem very much like the pipeline kind of thing that you can do, especially if I was able to parallelize one of those, gosh, that's difficult to say, things. It might break down in a way that I don't understand. The performance was not as good, and initially I thought it was because of that random number generator I'm creating per pixel. It's not free to make a Mersenne twister, but it turned out not to be that. We'll see why at the end. Let's move on to the data-oriented design. And for the one person who might recognize that, yes, this is the BBC Micro OWL that people of a certain age in Britain would have seen on their school computers. That's the problem with actually doing this kind of thing, incidentally, is that you get distracted making pretty pictures. And when you're a coder, this is the kind of quality of art you can come up with. I sat down, you should see the ASCII that I had to type in stars and spaces to make it. Very pleased. Anyway, the tenets of data-oriented design, as I understand them, are design around the most common operations, design your data by the access patterns to design the data by the access patterns, taking into account caching effects and things like that. Try and avoid branches or make the branches as predictable as possible. And as part of that, don't have polymorphic objects where you can essentially randomly determine functionality as you encounter each object. Separate things that can be separated so that you can have, well, let me show you. Oh no, sorry, forgot about this slide. I'll show you in a second. The changes that I made are basically determining that intersection was by far the most common operation. And a huge caveat here, no one in their right mind writes the kind of raycaster or the path trace that I've done here, because you would use some kind of acceleration structure to cull very quickly a large number of objects based on the direction of the ray and things like that. But I was actually sort of looking to see how much faster the data-oriented design would be, given that I'm going to give it a huge amount of objects to intersect with every single time. So anyway, the intersection is the most common operation by far. And the observation I made while I was writing this is that I actually only need the information about the nearest point. If a ray goes through a complicated scene, in the other two versions, I'm calculating this hit which has all of the extra information about the normals and things, and I might be throwing it away because it could be one that's off at a point at infinity. And I only have two types of object, so I can just separate them into all the spheres and all the triangles. This is what I mean by that. And even more, I've broken this down by the access patterns. So the very most common thing I do is intersect a line with a triangle. In order to intersect a line with a triangle, or a ray with a triangle, I need to, first of all, determine the point on the plane where the ray intersects with the plane of the triangle, and then determine whether or not that point lies inside the triangle. And it turns out that operation only needs the corners of the triangle. I don't need its material, I don't need its normals, I don't need anything else I might be storing with it. So I've separated that out into its own array. And then the other stuff is in parallel arrays. Similarly for the spheres, I have this sort of platonic sphere, and then for each sphere there is a material stored in a separate array. And then the intersection looks something like this. I'm going to count, like with an index. It was horrible giving up range 4. And I think I could do it. I think I was chatting with somebody about how we could make it work with a range 4. But ultimately, I'm trying to iterate through a bunch of arrays at the same time. And I'm going to do the maths. And if I didn't hit, I can skip this sphere. Oops. Otherwise, if this is the nearest sphere, just remember its number. I don't need to do anything else right now because there could be 20 more spheres in front of it that are nearer. And then I go around the loop. And the maths is fairly complicated, but the compiler loves this. It's got a very simple loop that it can look through and really do well with, so it optimizes it really well. If after all that we still didn't hit anything, well, we're finished. Otherwise, now we do that work to work out actually where the hit point is, what the normal is, whether we're inside the sphere and outside the sphere, all that good stuff. And at this point, we need to look up the material. So we only actually look at the material for the thing we actually hit. Similarly for triangles, loop over all the triangles, we calculate the u. The u is kind of the leftness and rightness of the point on the plane. So the triangle plane is set up so that 0 to 1 is like the spot where you'll be inside the triangle, anything else is outside of the triangle, and similarly for this v coordinate. So if u is less than 0, we're off to the left. If u is greater than 1, we're far off to the right. So we can skip. Otherwise, we calculate the other coordinate and check that. And then we check the distance, and then this is a bigger win actually because those normals on the triangle are quite big, and so doing all of the other calculations I needed to do just for the one triangle I hit is super. The rest is actually broadly the same. That's why I've just shown you that highlight of the intersection. What did I like about this approach? Well, the ability to optimize is great, right? It's the thing I like the most. And I like the performance until I really actually measured it properly. We'll see. What did I not like about this? Well, the testability went right down. I mean, I'm probably doing it wrong, and I would welcome anyone coming up and correcting me on this. But once I started making these kind of very low-level changes where I was separating out the data into separate arrays that were all held together, where I no longer had this nice sphere object I could just test the heck out of, and I no longer had this kind of sphere primitive that I could fire arrays at and make sure it worked. I had a scene that only worked by as a unit. And so all of my tests evolved to construct a whole scene, put a single sphere into it, and now fire arrays through the whole system and see if it hits in the right place. And that felt more like I was writing integration tests than I was writing individual tests. Now, again, I could be doing that wrong. Also, it was rather difficult to change. You know, the data patterns inside, the objects that you're working with obviously change the way that you're going to lay out stuff. And so if I needed to add a new type, if I decided to add, a cube as a primitive, then you can imagine in the OO, it's just I make a cube type and I chuck it in the list with everything else and it just works, right? And I tested the cube by itself, and that's great. Pretty similar in the FP case, although there are a couple of places where I might have to update the code for the variants that I'm using. But for here, I'd have to make a whole new array, and I'd have to write a whole bunch of code in the middle of the guts of the rest of the scene. And I'm going to be honest with you right now. My intention at this point was to go off on and now I'm going to put acceleration structures in and have bounding volume hierarchies and speed it all up and everything, and then I was going to show how difficult it would be to sort of retrofit this into the data-oriented design. But something happened. Before we get to that, what is my favorite? Well, all of them. I loved everything about all of this project. I learned so much about what it means to be functional. I learned how to use ranges or how to misuse ranges. I really got down in the weeds with the data-oriented design thing. That was a lot of fun. And I think we could all agree, C++ is best because we can blend all of these things together and use all the different styles of programming where it's appropriate. And not many other languages can say that, I think. Let's talk about performance. This is the machine I tested on, and this is all of the things you do when you're doing benchmarking. And I ran it multiple times, and they were always within 1 second of each other, so I'm only going to show like the results of one in this. So the first thing I did was look at this Cornell box scene. And this is a 256 by 256 image, 32 samples per pixel. And you can see how grainy the image is because this is partly the Monte Carlo thing going on here. In order to get it as nice as the pictures I showed at the beginning, I think I did something like 20,000 samples. It definitely pays to go multi-threaded at that point, incidentally. I've got a whole bunch of threading code. And you can rent these amazing 96-core machines off of Amazon. It's so much fun to play with. Just remember to shut them down when you're done with them, though. Just saying. So here we've got something that kind of makes sense to me, right? This is a very small scene. There's only one sphere. There shouldn't really be one sphere in there at all, but I couldn't resist myself. And there's 38 triangles. So all of this is going to fit in the probably L1 cache. So all the cool things I'm doing in the data-oriented design probably aren't going to make much difference at this scale. The functional is slower, and I'm not really sure why, although put a pin in that. But the fact that the OO and the data-oriented are the same is like, eh. The owl scene is all about those spheres. There's 100 of them in the scene, and only 12 triangles. Here, the data-oriented approach is starting to shine. We've got more information than can fit in the L1, and I don't know how about the L2 at this point. I didn't actually measure it. But you can see we've got like 96 seconds for object-oriented, started to take a bit of a hit. Functional, near enough the same. Very charitable. And data-oriented is just acing it here, and that's awesome. And at this point, I was going to go off and do my acceleration structures, prove how difficult it is to put it into DoD, and then that would be the end of the talk. But this happened. I tried this beautiful monkey. This is 970 triangles and 2 spheres. What on earth happened to the data-oriented design here? It is slower than the object-oriented. This is meant to be the thing that I was optimizing for. This is why I did all this work. It didn't work out the way I thought it did. And 2 weeks ago, when I gave the first version of this talk, it ended here because I didn't know what was going on, and I was in a state of utter despair, as I consider myself to be, well, no, somebody who knows these kinds of things, but I just couldn't work it out. Now, because we only have a relatively small amount of time left, I'm going to give you what should be the second hour of this talk in 10 minutes. Maybe they'll invite me back. So what happened? As I say, it took me about 10 days to work this out in the fullness, but we're going to give you a kind of condensed version. Who here knows about perf, as in the tool, the Linux tool? Yes, it's brilliant, isn't it? It's kind of the kitchen sink of what the heck's my program doing. In this instance, I ran the 3 different styles on the Suzanne scene under perf stat, which records all sorts of information about the CPU state. It records the number of CPU instructions that were retired, the number of branches that were predicted correctly, the number of branches that weren't, the cache state, all those kind of good things, and kind of presents you at the end with a big chunk of, this is like a breakdown of what happened. And it looked like this, or at least the important part I've cut out here. So 252 billion instructions for the object-oriented version, which is broadly the same as the functional, incidentally. That's 238 billion. But look at the data-oriented design. It definitely ran fewer instructions. It ran 150 billion instructions. It's funny to be talking in billions, isn't it? But that branch rate is the thing I want you to look at. 0.6% in the object-oriented case. That's kind of what I'd expect. From like playing around with the branch predictor and things like that, I've become so impressed with how well it performs under almost every circumstance that 0.6 is kind of, I take for granted, but just think about it. It's frankly clairvoyant of the branch predictor. If only we could get it to like predict lottery numbers or something. Although it hasn't done so well later on, has it? So let's look down at the functional version. Here we've got 5% of all branches were misses. That's a clue, actually, as to why the functional started to drop off before the DoD version went bonkers. So here, in this final set, the data-oriented design, 12% of all branches were mispredicted. So this is a multi-minute process here. I ran the thing for like 5 or 6 minutes, and through the entire execution of the program, more than 1 in 10 branches went the wrong way and sent the processor off in some kind of crazed thing before it went, oh, now I've got to go all the way back and start again. And that obviously is just no good. And it seems to be what causes the performance issue. So you won't be able to read this, but it's up here for sort of posterity, and maybe for those in the YouTube can zoom in. These slides will be available anyway. But this is a capture of me doing a recording of where the branch misses happened. And on the most recent Intel chips, you can actually enable a mode where you can count precisely where the misses happened. Although this is what I was staring at 2 days into my 10-day long navel gaze over what on earth was going on, because what I hadn't realized is that the place where the branch is marked as having been mispredicted is actually the correct destination, the corrected destination of the branch, not the branch instruction itself. So what you can see here, this yellow line is highlighting a branch. The next line underneath it has, and I can't even read it, 44% of the time, it had to be re-steered back to this point. Like that branch was mispredicted above, and it went whoops, and came back to here. If we look at the destination, which is the second from bottom, that also has 46% of the time. So 46% of the time it fell through the branch and was wrong. 46% of the time it took the branch and it was wrong. So that's pretty much an unpredictable branch somehow, right? I mean, but what is it? I tracked it back to the triangle code, no surprise. So if you remember, this is broadly what the triangle code looks like. There's this calculation of the U position, and it amounts to this. We do a comparison with 0, and if it's less than 0, then we branch off to the continue, and if it's more than 1, we branch off to continue, or sorry, I've called it skip here. This is the thing which jumps to back and goes round the loop to the next iteration. Is anyone sort of starting to wonder seeing anything? There's any nods in the crowd? No, really? Well, let's take a look at my appalling diagram that I put in at the last minute. This is like what the triangle might look like. And think we're casting essentially completely random rays around this scene. And these triangles are tiny, and there are loads of them. The chances of any one ray ever actually intersecting with a particular triangle is diminishingly small. But the chances of the ray intersecting with the plane that the triangle is on is almost 1, right? Unless they're absolutely coplanar, there will be some point, probably off 100 miles away, where a ray is colliding with or is intersecting with the plane. So that X there, the little ray plane intersection point, is totally random. So the chances of it being less than 0 are random 50-50. The chances of it being greater than 1 are random 50-50 and almost totally anti-correlated with the first. It's only if the ray happens to be in the triangle that the branch should be skipped in this case. So to summarize, U less than 0 is unpredictable, U greater than 1 is unpredictable. But if I was a betting man, I'd say that the combined comparison of them, like did this miss, is pretty predictable. You could just guess that it does miss. Moreover, you should be able to predict, like if I actually combine the U and the V and say if this is inside the triangle, that should just be like, yeah, it's never inside the triangle. And I'll take the hit the occasional times that I'm wrong and come back and do the work for when I'm actually hitting a triangle. You may notice there's an asterisk on the should be predictable. This is very specific to the compiler. The compiler has a choice when it's doing this comparison, when it has a sequence of comparisons. If it knows that there's no side effects in the expressions that are ORed together, it could choose to combine them and run them all anyway. But obviously, most of the time, if you're doing a logical OR, as soon as one of them is true, the compiler is kind of forbidden for looking at the remaining things. So it kind of has to use the U is less than 0 first, and then the U is greater than 1, unless it can prove there's no side effects. Of course, there are no side effects. And so I moved the code around a little bit to make it look like this. and I was actually waiting outside my son's school to see his teacher, so I had my laptop open and I was hacking away, and I managed to get it to go super fast, which you'll see in a second, and I was so excited. I closed the laptop lid, I had my parent-teacher conference, and then I came back out, and I tidied up the code and checked it in. And then the next morning, I checked it, and it was slow again. And I thought, did I hallucinate that? Am I really going, I mean, maybe I dreamt it. And what had happened is that when I'd combined them the first time round, and I was sort of git stashing and git unstashing to sort of compare a before and after, I'd combined them, but I hadn't done them this way round. I'd actually put the check of v is less than 0 first. And for whatever reason inside the compiler, that triggered it to combine all those conditionals into one. But when I looked at it to check it in, I went, oh, it's so much nicer to write it u is less than 0 or u is greater than 1 rather than the v check. And that tripped it up, and it decided to use lots of jumps again. So it's really sensitive. So I did this. Oh. I'm now using a bitwise OR, and that basically ties the compiler's hands a little bit. So the compiler has to do these conditions separately, and if it knows what's good for it, it'll use a CMOV or something similar. And then it ORs them all together, and then that's the thing that I make the decision on. Oh, let me show that concretely. So it looks a bit like this. It's horrible. So I'm actually doing more work, right? I'm always calculating u and v, and then I'm using this horrible bitwise OR trick. But it makes it 36% faster. So the fact that we go from several unpredictable branches back to back to a bunch of extra work all the time, and then one predictable branch made all the difference here. Oops. So I backported it into all of the other styles, and you can see that mostly they got better as well. So that now the FP and the OO and the DOD in that Cornell scene, that top line, they are broadly as I would have expected. You know, there's nothing fundamentally different with functional programming versus object-oriented programming. That's great, right? There I was thinking it was like some problem with the range library or some problem with me making these Mersenne twisters. No, it was the branch predictor all along. The OWL has stayed broadly the same. Because I'd already made this change. Sorry, this is a bad line. Unfortunately, the OO version, well, I never really understood why it didn't suffer from this the first time round, and I can just wave my hands and say I haven't had time to work it out. And more puzzling, something which happened when I was redoing all of this in my hotel room earlier this week, is that the Suzanne monkey is now actually slower than it was before on the OO with this trick. So I guess the takeaway from this is that there's a load of really cool and interesting things that go on inside your CPU, which is not the talk you came to, I know. And it's subtle, and the compiler gods are quick to anger, as is the branch predictor. So this needs more work. If I had more time, both to develop the code and to talk, I'd go into a lot more detail on some of the other interesting things I found along the way. As I say, the code's on GitHub, and I encourage you to take a look. I have got threading in here, and I tried using stood futures, and that was a lot of fun until it wasn't. I had a bunch of devirtualization slides that I had to take out because the compilers, as I say, I know there I was giving them a hard time a minute ago, but they really do amazing things these days. Future directions, it annoys me that I don't support transparency. That's like the number one thing to do, isn't it, is to have a nice transparent sphere somewhere in your ray tracing demo. I would have liked to have put that in. I'd have loved to have made the monkey, the Suzanne monkey, made out of jade. There's some amazing things you can do with like subsurface scattering, and it's such an amazing and interesting topic, computer graphics. And I realize I'm a total amateur, so I'm aware there may be people in here whose job it is to do this all day. I would have loved to actually go back to the data-oriented design and spend more time on it. One of the limiting factors I've got here is that because I was using the vector3 class, that ties x, y, and z together. And maybe actually I should have parallelized that array as well and had x, 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 all the triangle x's, all the triangle y's, and all the triangle z's, and then perhaps been able to use more SIMD type things. But again, that really starts to tie you into a particular implementation, cool though it is. An early version of the code, incidentally, I developed while I was on a break between jobs, and I was live streaming it all. So I'd like to say a big thank you to all the people who came onto the YouTube channel and offered advice and emailed me afterwards, and had some, in particular, Luca was awesome, so I want to say thanks to them. And really, I guess my conclusion is Go learn your own language. Go and pick something cool that you like to do. Make it a Mandelbrot, ray tracer, emulator, sound generator, anything. Go and use it and have fun, because programming is fun, right? Seems I have 5 minutes if anyone has any questions or comments. No. Is anyone from the games industry or the rendering industry going to tell me how I'm doing it wrong? Oliver in the front row's raised his hand, but I think he's just being silly. Okay, well, thank you all for coming. I've really appreciated this opportunity to talk to you all.